Welcome to our discussion on exponential functions. Be sure that you have reviewed the homework for 2.0, which goes over all the exponent rules that are necessary to succeed in this section. Let's start by introducing the exponential function. What does it look like? What doesn't it look like? So, by definition, what the exponential function looks like is a function of this form. Sometimes this function can be often rewritten just to make things a little bit more obvious, which we will do together, as c times b to the x. The reason why I like this form is it really helps isolate that exponent right here in the input spot, our x, as only acting on that base value, that b value, right? And so how I identify an exponential function is I simply look for the placement of my input, right? Remember, the x is our input variable. When the input variable is in the exponent spot, that's one of the key telltale signs for me, right? So input is in the exponent spot. That's how I know I'm looking at an exponential, right? So exponentials do have some restrictions on them. One of the first one being is that base value is going to be bigger than 0. We also don't want it to be equal to 1. And we don't want our c value to be equal to 0, or else we're multiplying by 0 and nothing really interesting happens, right? And so looking at the parts of this, right, the c value is called our initial value, and this b value is called our growth factor or base. So either one, right? And then the domain of all exponentials is all real numbers. So in interval notation, domain is all numbers from negative infinity to positive infinity. Basically, you can plug anything in, right? And so the reason why this is called our growth factor, essentially, when we are working with our input, we're going to be multiplying values over and over and over, which means we have two types of exponential functions. So two types of exponential functions. The first one being growth, exponential growth, and the second one being decay. So before we get started and we talk about the differences between these two and their similarities, I guess, is basically an exponential versus non-exponential function, right? So something that is an exponential function will look something like this, right? So these are exponentials. So like f of x equal to 2 to the x, pretty common one that we spend a lot of time talking about. We definitely compare it commonly to this exponential function, 1/2 to the x. We can get a little bit more creative than this though, right? So we can have another function. We won't get creative with the names. We could have, an initial value of 500, and then maybe we're tripling our inputs every time, right? And then these values, they don't have to be whole numbers. They don't have to be fractions. They could be decimals, as long as they meet the restrictions where the base is bigger than 0 and not equal to 1, stuff that we talked about. So for example, you could have a function that looks like this, 0.75 times 1/2 to the x. Or maybe you have another one that looks like this. I don't know, 500 times 2.4 to the x. I kind of feel like I made that look like a decimal. Let's bring that up. Right, so that's another example. We'll call this one h of x. And it doesn't have to be x. So anything that's non-exponential, essentially any other type of function, right? Like our polynomials, like we saw in the previous section, x squared plus 2x. Our linear functions, 2x minus 1. A log function, which we'll explore more later. Trig functions. The most commonly confused functions are this one, x squared and 2x. Most commonly confused. One's an exponential, one is not. In fact, this one is a polynomial or quadratic. And so now that we know what isn't and what isn't an exponential, let's talk about their graphs, what they look like. Let's talk about these two types before we jump in. We have our two types, growth and decay. They can be identified both algebraically and from the graph. Let's draw the graph first. Remember, we read all graphs from left to right. So an example of growth over time looks something like this. An example of decay from left to right, meaning our outputs are quickly getting smaller. Right? So one is an example of outputs getting bigger. One is an example of outputs getting smaller, right? So like always reading our graphs in one direction. So output. So these can also be identified, the type of function. So for our growth, we're going to have a base bigger than 1, right? So for example, our 2 to the x, our 2.75 to the x, our 500 times 3 to the x. I mean, as long as this value right here that's acting on that x is bigger than 1. That's all we need. Even if the other value is a decimal, so like 0.05 times 6 to the x. I don't know, I'm making things up at this point, right? As long as that base value, 6, is bigger than 1, we will have growth, right? Maybe it's slower growth, maybe not. Depends on some values we'd have to double check. But either way, growth over time. For decay, we're going to look at bases that are less than 1. So like our 1/2 to the x, our 500 times 0.75 to the x, right? Doesn't matter how big or small this value is. What we are looking at is when this base is less than 1. We also need to keep our restrictions in mind that the base can't be equal to 1, which is why you see no equal sign here, or else you get essentially something where the base is equal to 1. Just looks like a straight line. No longer exponential, no growth, no decay, it's linear. Not very interesting, right? So that's why we restrict it. And then negatives, a little bit more detail as to why it can't be negative. So we'll go ahead and just restrict that to be between 0 and 1.